the Milky Way. For over a century, humanity has been unintentionally broadcasting its presence into the cosmos. Structured radio signals from Earth have traveled outward at the speed of light, reaching many nearby stars and potentially thousands of light years beyond. These signals could already be present on the surfaces of potentially habitable exoplanets, such as Ross 128b or Gliese 667cc. Yet the closest stellar neighbor to the Sun remains the triple system Alpha Centauri, at a distance of 4.36 light years. For this reason, it stands as the most logical candidate for humanity's first interstellar mission. We begin our journey at this nearby system. Alpha Centauri consists of 3 stars. The 2 brightest components, Alpha Centauri A and B, orbit each other along weakly elliptical paths, completing one revolution in approximately 80 years. Their maximum separation reaches 35 astronomical units, while the minimum distance is about 11.2 astronomical units. Alpha Centauri A is the most massive and luminous of the pair. It is a main sequence star with a mass 8% greater than the Sun's and a radius 1.22 times larger. Its surface temperature and spectral class are very close to solar values, yet it radiates 1.5 times more energy than our Sun. No confirmed planets have yet been detected around Alpha Centauri A. However, infrared observations conducted in 2021 revealed tentative evidence of a possible planetary body with a mass between 9 and 35 Earth masses and a size between 3.3 and 7 Earth radii. This candidate would orbit at 1.1 astronomical units with a period of roughly 1 year. These findings still require confirmation by the James Webb Space Telescope or dedicated ground-based observatories. The second component, Alpha Centauri B, also known as Ptolemy, is likewise a main sequence star, but its mass is 10% less than the Sun's, and its radius is 0.86 times solar. Its surface temperature is approximately 5,260 Kelvin, giving the star a distinct orange hue and making it roughly half as luminous as the Sun. Compared with other stars of its class, it emits significantly more energy in the X-ray range and exhibits frequent surface flares and powerful outbursts. No confirmed planets have been identified around Alpha Centauri B either. A 2012 claim suggesting a close-in planet with a 3.2-day orbital period was later shown to result from a mathematical error in the data analysis. The third component differs markedly from its companions. Proxima Centauri is a red dwarf with only 12% of the Sun's mass and a diameter roughly 7 times smaller. Its surface temperature is just over 3,000 Kelvin, and its luminosity is a mere 0.1% of the Sun's. At 4.25 light years, it is the closest known star to the Sun. The distance continues to decrease gradually and will reach just over 3 light years in 26,700 years. Because of its extremely low brightness, Proxima remains invisible to the naked eye from Earth. Proxima is currently separated from the other 2 stars by 13,000 astronomical units, or 0.21 light years. Over the next 300,000 years, this gap will shrink to 4,100 astronomical units. A complete orbit around the system's common center of mass takes 547,000 years. Unlike its brighter companions, the Proxima Centauri system contains 2 confirmed exoplanets and evidence suggesting at least one additional candidate. Infrared studies also indicate the possible presence of a dust ring and numerous smaller bodies, such as asteroids and comets. The first confirmed planet, Proxima Centauri b, was discovered in 2016 by the radial velocity method and confirmed in 2020 through spectroscopic observations with the Very Large Telescope. It orbits at approximately 0.05 astronomical units from its star, completing one revolution in 11 Earth days. Its mass is 10 to 20% greater than Earth's, and its radius is about 1.3 Earth radii. Mathematical modeling shows that Proxima b receives roughly 1.5 times less stellar energy than Earth receives from the Sun. Its average surface temperature is 234 Kelvin, or minus 39 degrees Celsius. This raises the possibility that liquid water could exist in certain regions. However, the planet is most likely tidally locked, with one hemisphere permanently facing the star. Proxima Centauri is a highly active red dwarf that produces frequent, powerful flares and intense stellar wind outbursts. These events are believed to gradually erode the atmospheres of nearby planets. A strong planetary magnetic field could provide protection, but current assessments suggest the probability that Proxima b possesses one is extremely low. In 2020, the existence of a second planet, Proxima Centauri c, was confirmed. It orbits at about 1.5 astronomical units, with a period slightly longer than 5 years, and has a mass between 5 and 8 Earth masses. Depending on its exact size, it may be classified as either a mini-Neptune or a super-Earth. Due to its large distance from the star, surface temperatures are extremely low, approximately 39 Kelvin, or minus 234 degrees Celsius. Some observations also suggest the planet may possess a ring system. Analysis of recent Very Large Telescope data further hints at the possible existence of a third, very small exoplanet with a mass of roughly 0.25 Earth masses, orbiting at 0.29 astronomical units. If confirmed, its orbital period would be only about 8 Earth days, and its surface temperature would reach 360 degrees Celsius. The reality of this object, however, remains uncertain and requires additional verification. Alpha Centauri has been receiving Earth's radio signals for more than 100 years, yet the intervening 40 trillion kilometers of empty space still present an insurmountable barrier for current technology. Even light itself requires more than 4 years to cover the distance. Present-day spacecraft would need tens of thousands of years to make the journey. Nevertheless, advanced concepts such as the Breakthrough Starshot program propose sending a fleet of 1,000 microprobes on light sails, accelerated by powerful ground-based lasers. These probes could reach 20% of the speed of light, arriving in approximately 20 years, with the collected data returning to Earth roughly 5 years later. The modeling of distant planets remains a demanding yet essential scientific endeavor, made possible only by modern computational capabilities. By galactic standards, the region surrounding the solar system is sparsely populated. Nevertheless, within a radius of 15 light-years from Earth, astronomers have identified approximately 50 star systems containing a total of 65 stars. Many of these systems host exoplanets and protoplanetary disks. To examine this diversity, we gradually move outward from the Sun, crossing tens of light-years of interstellar space and visiting numerous distant worlds. Our first destination is Barnard's Star, a small red dwarf located 6 light-years away. It is notable for its exceptionally high proper motion, capable of crossing the moon's disk in 180 years. This rapid apparent motion results both from its proximity and from its approach toward the solar system at more than 100 kilometers per second. In approximately 10,000 years, Barnard's Star will become our nearest stellar neighbor at a distance of 3.8 light-years. Even then, its faint glow will remain invisible without optical aid. The star's mass is 17% of the sun's, and its radius is roughly 6 times smaller. Like other red dwarfs, it is cool, with a surface temperature of 3,134 Kelvin. Its luminosity is 2,300 times fainter than the sun's. After 2 decades of precise astrometric measurements, 2018 data provided evidence for a possible cold super-Earth with a minimum mass of 3.2 Earth masses. The planet would orbit at 0.4 astronomical units with a period of 233 days. Its orbit does not produce transits, making direct spectroscopic study difficult. Modeling nevertheless indicates that the planet receives 50 times less energy than Earth. Surface temperatures are estimated at 105 Kelvin, or minus 168 degrees Celsius.
Tidal heating or internal radioactivity could potentially maintain a subsurface ocean. Given that Barnard's Star is more than 10 billion years old, among the oldest stars known, any life in such an ocean would have had ample time to develop. Because of its proximity and favorable trajectory, Barnard's Star remains a high priority target for future interstellar exploration. On the opposite side of the Sun lies Sirius, the brightest star in Earth's night sky, at a distance of 8.6 light-years. Although it appears single to the naked eye, Sirius is a binary system. The 2 components are currently at their widest separation of about 30 astronomical units. Sirius A is a luminous, white-blue main sequence star. Its diameter is 71% larger than the Sun's, and its surface temperature reaches 9,940 Kelvin, allowing it to radiate 25 times more energy than our Sun. Sirius B is a white dwarf with a radius of only 6,000 kilometers. Its mass is nearly solar, but its density is extremely high, and its surface temperature is 25,000 Kelvin. Because of its small size, it is approximately 1,000 times fainter than its companion. Extensive searches have found no evidence of planets in the Sirius system. One explanation is the system's relative youth. Another possibility is that roughly 120 million years ago, Sirius B evolved into a red giant, shed its outer layers, and destroyed the surrounding protoplanetary disk. The 2 stars now orbit their common center of mass with a 50-year period. Over the next 60,000 years, Sirius will gradually approach Earth, increasing in apparent brightness, before slowly receding again over the following 660,000 years. Leaving the Sirius system, we travel to the red dwarf Wolf 1061, 14 light-years from Earth. Its radius is 30% of the Sun's, its mass is 1/4 solar, and its surface temperature is 3,000 Kelvin. The star is too faint to be seen with the naked eye. Despite its modest appearance, Wolf 1061 hosts one of the richest planetary systems among our nearest stellar neighbors. 3 rocky planets,
each similar in composition to Earth, yet possessing markedly different surface conditions. The innermost planet, Wolf 1061b, orbits at 0.037 astronomical units with a period of 5 days. Its mass lies between 1.5 and 2 Earth masses, and its radius is 20% larger than Earth's. It is likely tidally locked. The day side is extremely hot, and stellar flares, together with intense stellar wind, make the existence of an atmosphere improbable. Conditions are incompatible with life. The second planet, Wolf 1061c, orbits at 0.089 astronomical units with a period of 18 days and lies within the star's habitable zone. This super-Earth is 3 to 4 times more massive than our planet and has a radius approximately 1.6 times Earth's. Surface gravity is estimated to be 60% higher than on Earth. It receives less stellar energy than Earth, resulting in an equilibrium temperature of about 223 Kelvin, or minus 50 degrees Celsius. With a sufficiently dense atmosphere and greenhouse effect, liquid water could exist, and conditions might approach habitability. Among currently known potentially habitable exoplanets, Wolf 1061c ranks 5th in proximity to the solar system. The third planet, Wolf 1061d, follows a highly eccentric orbit ranging from 0.21 to 0.73 astronomical units, with a period of 217 Earth days. Its mass is approximately 7.7 Earth masses. If rocky, its radius would be about 1.7 Earth radii. If a mini Neptune with a thick atmosphere, its diameter would be at least 2.2 times Earth's. The planet never enters the habitable zone. While life is unlikely, the system offers valuable insights into planetary evolution and remains a priority for future study. Wolf 1061 lies near the boundary of the local interstellar cloud, a region of hot but extremely tenuous hydrogen gas at approximately 7,000 Kelvin, containing only 0.3 atoms per cubic centimeter, roughly half the average density of the Milky Way. The solar system has been traveling through this cloud for the past 10,000 years and is currently near its edge. Alpha Centauri has already entered the adjacent G cloud. We will remain inside the local cloud for another 2,000 years before passing into a still more rarefied region. Continuing outward, we encounter the star AP Columbae at 27.4 light-years. This red dwarf formed only 40 million years ago, long after the extinction of the dinosaurs on Earth. Young stars typically remain near their birth clusters for hundreds of millions of years. Proper motion studies suggest AP Columbae was once a member of such a cluster. A supernova explosion several million years ago appears to have imparted a strong velocity kick, ejecting the star from its original group. Despite its small mass of only 0.12 solar masses, AP Columbae radiates 4 times more energy than expected for a star of its size, and possesses a radius twice the theoretical value. The explanation lies in its unusually high lithium content, an element that is abundant in protostellar material, but rapidly consumed once nuclear fusion begins. This indicates that the star is still in an early, pre-main sequence stage of evolution, and has not yet achieved stable hydrogen fusion. Consequently, it is unstable and subject to strong flares, during which its brightness can increase by a factor of 10. Such flares would pose a severe threat to any nearby planets by stripping atmospheres and irradiating surfaces. However,
No large bodies have been detected within 4 astronomical units, consistent with the star's youth. AP Columbae, therefore, serves as a valuable laboratory for studying the earliest phases of stellar evolution. Not every star is accompanied by planets. Our next destination is the orange dwarf Gliese 370, 37 light-years from Earth. In 2011, a single exoplanet, Gliese 370b, was discovered using the radial velocity technique. Its mass is between 1 and 2 Earth masses, and it is believed to be a rocky world with a radius approximately 30% larger than Earth's. Surface gravity is therefore at least 40% higher than on Earth. The planet orbits at 0.26 astronomical units, with a period of 544 Earth days, and lies within the habitable zone. Assuming an Earth-like albedo, its average surface temperature would be approximately 25 degrees Celsius. Because it is sufficiently distant from its star, it is unlikely to be tidally locked and should experience a regular day-night cycle. Moderate gravity would tend to smooth topographic relief, while abundant liquid water could form extensive, warm, shallow seas, environments widely regarded as favorable for the origin and development of life. At discovery, Gliese 370b was considered one of the most promising candidates for habitability. Subsequent studies have indicated that its atmosphere may be dense and possess a strong greenhouse effect. Even under pessimistic assumptions, however, average temperatures would not exceed 78 degrees Celsius, with a surface range of roughly 30 to 100 degrees Celsius. These conditions resemble those of Earth during the Archean eon. Consequently, Gliese 370b continues to be an important target for future observations. At this point, we have traveled more than 50 light-years from the solar system. Within this volume, more than 1,000 stars are known. While most are single, some form binary or multiple systems. A striking example is Castor, a complex sextuple system 50 light-years away that appears as a single bright star to the naked eye and is the second brightest object in the constellation Gemini. The system's architecture is intricate. Castor A and B are white-blue stars resembling Sirius, each accompanied by a close red dwarf companion. The distance between the centers of these pairs is approximately 110 astronomical units, and their mutual orbital period is 445 years. Roughly 600 astronomical units farther lies another tight binary, consisting of 2 nearly identical red dwarfs, each with 0.6 solar masses and surface temperatures near 3,900 Kelvin. These 2 stars orbit each other in less than 20 hours, while the entire system revolves around the common center of mass, with a period of about 14,000 years. No confirmed exoplanets have yet been detected in the Castor system. Should any exist, they would most likely be found near the faintest component, Castor C. In 2019, variations in Castor C's orbital period were observed, suggesting the possible presence of a brown dwarf, approximately 49 times the mass of Jupiter, orbiting at 14 astronomical units, with a 54-year period. Like many red dwarfs, Castor C may also host close-in rocky planets. From the surface of such a hypothetical world, the sky would present 2 prominent crimson suns moving across the heavens, their combined light hundreds of times brighter than the moon. Although the stars we have visited are separated by vast distances, they all belong to a single coherent structure, approximately 300 light-years in extent, the local bubble. This region contains not only stars, but also large-scale interstellar features, including the local interstellar cloud. The local bubble itself formed from the successive explosions of several supernovae between 10 and 15 million years ago.
It consists of a giant volume of hot gas at temperatures of millions of Kelvin. The high temperature causes the gas to expand, resulting in a density roughly 10 times lower than the galactic average. The hot, ionized hydrogen within it emits X-rays, yet the combined protection of the Sun's magnetic field, Earth's magnetic field, and our planet's atmosphere effectively shields us from this radiation. The local bubble borders other similar structures. One example is the loop bubble, formed by supernovae near Antares. Long-term interaction between these two giant cavities has produced dense compression zones at their boundary. The center of the neighboring bubble lies approximately 500 light-years away. In several tens of millions of years, the solar system will reach its outer edge. Clouds of hot gas, scattered stellar clusters, giant nebulae, and stellar streams together constitute the building blocks of galaxies. Galaxies in turn connect to form immense filaments, streams, and walls spanning billions of light years. In this way, the large-scale structure of the universe takes shape, concealing countless stars and worlds within its depths. The theoretical foundation for the existence of planets entirely covered by water was first established in the 1970s. It was then demonstrated that radioactive decay in planetary interiors can melt water ice and generate enormous subsurface oceans. Similar processes are thought to occur beneath the icy crusts of certain moons of Jupiter and Saturn. On true ocean planets, however, the water layer is expected to be hundreds of kilometers deep. Detailed calculations of the formation and evolution of such worlds were published in 2004 by a team of French astrophysicists led by Christophe Sautin. According to their models, a forming planet with a mass exceeding 10 Earth masses will accrete large amounts of hydrogen and helium and become a gas giant. A planet with a mass of 6 to 8 Earth masses, by contrast, will consist of roughly equal parts ice and rock. For reference, all the water in Earth's oceans constitutes only 0.025% of our planet's total mass. If such a planet orbits far from its star, it becomes an ice giant or cold super-Earth with a buried ocean. If it lies within the habitable zone, the outer ice layers melt, producing a global ocean. The pressure at the base of a water column hundreds of kilometers deep can reach 20,000 atmospheres. Under these conditions, exotic high-pressure ices, such as Ice 7, remain solid even at elevated temperatures. Ice 7 has a density of approximately 1,650 kilograms per cubic meter and settles at the bottom, forming a thick cryosphere surrounding a denser, rocky metal core. Observational confirmation of this theoretical picture became possible with the discovery of the faint red dwarf Gliese 1214, 42 light-years from Earth. The star itself is unremarkable. Its diameter is 5 times smaller than the Sun's. Its mass is 15.7% solar. It is 300 times fainter than the Sun, and its surface temperature is 3,000 Kelvin. In 2009, a single planet, Gliese 1214b, was found orbiting this star. Although its diameter is 2.7 times Earth's, its mass is only 6.5 times greater. Surface gravity is therefore 91% of Earth's. The average density of 1,870 kilograms per cubic meter is too low for a purely rocky composition, and instead matches a world that is 3/4 water and water ice and 1/4 rocky material. The planet orbits extremely close to its star, only 0.014 astronomical units, or 75 times closer than Earth to the Sun. Its orbital eccentricity is 0.27, and its period is 36 hours. Despite the star's low luminosity, the extreme proximity produces high surface temperatures, ranging from 120 degrees Celsius, assuming Venus-like albedo, to 280 degrees Celsius, if darker. Because the orbit transits the star, the atmosphere can be studied spectroscopically. Results to date are inconclusive. If the planet is indeed an ocean world, its atmosphere should be dominated by water vapor. However, no clear spectral lines of water, hydrogen, or other expected molecules have yet been detected, suggesting that a dense upper haze layer may obscure the true composition. The surface environment resembles the interior of a giant pressure cooker. Atmospheric pressure in the lower layers is at least 15 times higher than on Earth. The ocean atmosphere boundary is diffuse, with water vapor density near the surface comparable to that of boiling water. As depth increases, pressure rises rapidly. At approximately 100 kilometers, the water can no longer remain liquid and transforms into dense ice 7, whose layer may exceed 5,000 kilometers in thickness. Below this cryosphere lies a core of rock and metal. The formation of life on such ocean planets is considered improbable even under more temperate conditions, primarily because of the scarcity of essential microelements. Nevertheless, these worlds remain of great scientific interest. Models published by NASA in 2020 estimate that billions of similar planets, both cold, ice-covered ocean worlds, and warmer ones like Gliese 1214b, may exist throughout the Milky Way. Water is one of the fundamental ingredients of the universe, and the prospects for discovering additional ocean planets are therefore substantial. 50 light-years from Earth lies the red giant CW Leonis, also cataloged as IRC plus 10,216. If placed at the center of the solar system, its surface would extend beyond the orbit of Mars and reach the inner edge of the asteroid belt. Although its mass is only 0.8 to 1.5 solar masses, the star radiates 8,500 times more energy than the Sun because of its enormous size. CW Leonis is in the final stages of its evolution. It is believed to have begun as a white-blue star of 3 to 5 solar masses. Roughly 1 billion years ago, hydrogen in its core was exhausted and converted to helium. Internal pressure caused the outer layers to expand dramatically, changing the star's color to deep red. At present, the star contains large quantities of carbon, but lacks sufficient mass to ignite further fusion stages. Thermonuclear reactions in its interior have become unstable. The star pulsates with a period of 649 days. At maximum, it is 11,300 times more luminous than the Sun. At minimum, 6,250 times. During contraction, the upper layers are partially ejected, feeding a surrounding carbon-oxygen nebula. The mass loss rate is approximately 4 times 10 to the minus 7 Earth masses per second, equivalent to about 400 Earth masses per year. The nebula is at least 69,000 years old,
has a mass of roughly 1.5 solar masses and extends to 8 astronomical units. Its complex structure of clumps, rings, and thickenings is shaped by the star's magnetic activity and strong stellar wind. Spectral analysis reveals approximately 70 different chemical compounds within the nebula, including carbon dioxide, water, and ammonia, as well as heavy elements up to iron. It is possible that planets once orbited CW Leonis, but were engulfed during the giant phase. However, observations in 1994 and 2017 detected small orbital perturbations and material displacements that may indicate the presence of a low-mass red dwarf companion with an orbital period of about 100 years. A notable feature is the relatively high water content in the star's outer layers. Earlier models predicted that all available oxygen should have combined with carbon to form carbon monoxide. Current understanding suggests that intense ultraviolet radiation breaks apart oxide molecules, allowing freed oxygen to react with hydrogen and produce water vapor. The total mass of water vapor is estimated at several quintillion tons, still only 1/1000th of the star's overall mass. According to present stellar evolution models, CW Leonis has between 10,000 and 30,000 years remaining as a red giant. It will then eject its outer envelope in a final outburst and collapse into a white dwarf with approximately 80% of the Sun's mass. Without a nuclear energy source, the white dwarf will cool slowly over billions of years, eventually becoming a cold black dwarf. This final stage, however, lies far in the future. The shock wave and extreme temperatures of the terminal explosion will synthesize elements such as uranium, gold, and lead that cannot be produced inside ordinary stars. These newly formed elements will later be incorporated into new planetary systems. Radioactive decay will heat planetary interiors, melt ices, and enrich oceans with the chemical building blocks necessary for life. The evolution of the universe depends on such dramatic events. After every cosmic catastrophe, new possibilities emerge. We have already examined several extreme and inhospitable worlds. Our survey of the most hostile planets, however, is not yet complete. Our first stop lies 2002 light-years from Earth, near the orange dwarf K2-141. The planet K2-141b orbits at only 0.007 astronomical units. Its mass is approximately 5 times that of Earth, implying surface gravity at least twice as strong. The orbital period is 6.5 hours, and the planet is tidally locked. Temperatures on the day side reach 3,270 Kelvin, or 3,000 degrees Celsius, hot enough to vaporize rock and metal. The day side is believed to feature a perpetual lava ocean and an atmosphere composed of metal and silicate vapors. The night side is drastically colder. The extreme temperature gradient drives supersonic winds, reaching 1.75 kilometers per second. Atmospheric material that reaches the night side condenses and falls as molten metal rain, creating lava rivers that return material to the dayside ocean. This creates a continuous cycle of evaporation and precipitation, confined largely to the boundary zone. The central region of the night side remains a frigid, frozen landscape. Yet even K2141b is not the hottest known exoplanet. At 670 light-years lies KELT9b, whose surface temperature is 4,600 Kelvin, or approximately 4,330 degrees Celsius, hotter than the photosphere of some stars. Its host star, KELT9, is a white-blue giant 2.6 times more massive than the Sun, with a diameter 2.3 times solar
and a surface temperature of 10,170 Kelvin. The planet orbits at a distance of only a few thousandths of an astronomical unit and completes one revolution in about 1.5 days. It is a hot gas giant more massive than Jupiter. Atmospheric temperatures may reach 11,000 Kelvin, sufficient to ionize heavy metals. Iron and titanium vapors have been detected. Intense stellar wind is steadily eroding the atmosphere at a rate of 6 to 8 Earth masses per billion years. Over time, the planet could lose its entire gaseous envelope. These examples illustrate that stars can both nurture and destroy the worlds around them.
Some planets, however, have survived the most violent phases of their parent star's evolution. One such world is V391 Pegasi b, orbiting the white dwarf V391 Pegasi, 4,000 light-years from Earth. The white dwarf has half the Sun's mass and 23% of its radius, with a surface temperature near 30,000 Kelvin. Thermonuclear fusion ceased long ago. The star will slowly cool into a black dwarf over hundreds of billions of years. The planet V391 Pegasi b not only survived the red giant phase of its progenitor, but appears to have moved within the star's outer layers for a time. During that phase, the outer envelope was extremely tenuous, tens of times less dense than Earth's atmosphere, allowing the planet to retain structural integrity. It is now a gas giant, approximately 3 times the mass of Jupiter, orbiting at 1.7 astronomical units with a period of 170 Earth days. The precise mechanism that enabled it to preserve so much mass remains unclear, but the progenitor's collapse clearly altered both its orbit and physical characteristics. The cosmos contains many objects whose properties are difficult to observe in visible light, but readily detectable at radio wavelengths. Pulsars provide a classic example. It was through radio observations that astronomers discovered a planet orbiting the millisecond pulsar PSRB 1257 plus 12, located approximately 4,000 light-years from Earth. The pulsar itself is only 20 kilometers in diameter, yet has 1.4 solar masses. It rotates at roughly 10,000 revolutions per minute and emits powerful beams of electromagnetic radiation. These beams continuously irradiate the planet's surface, creating extremely hostile conditions. The planet completes one orbit in only 2 hours at a distance of 0.004 astronomical units, less than the Sun's radius. Surface gravity is approximately 20 times stronger than Earth's, and the average density is 23 grams per cubic centimeter. The composition is believed to be dominated by crystalline carbon under extreme pressure, with upper layers possibly containing carbon-rich silicates. It is highly unlikely that the planet could have survived the supernova explosion of its progenitor star. It most probably formed after the pulsar was already present. An alternative suggestion is that the object is the remnant of a white dwarf that lost most of its mass. In either case, this world ranks among the most extreme and inhospitable environments known. Objects that absorb all incident light are inherently difficult to detect. Consequently, only a modest number of confirmed black hole candidates are currently known. Theoretical models nevertheless indicate that the Milky Way
may contain as many as 100 million black holes.
Given that the galaxy holds between 200 and 400 billion stars, black holes remain comparatively rare. A star must possess at least 18 solar masses at the end of its life for its core to collapse into a black hole following a supernova. Only then is the resulting density sufficient to prevent even light from escaping the Schwarzschild radius. Beyond this boundary, the physics we understand no longer applies. One of the nearest known black holes is A0620-00, also designated V616 Monocerotis, located 3,300 light-years from Earth in the constellation Monoceros. It forms a binary system with an orange dwarf of approximately 0.5 solar masses. The dwarf completes an orbit every 7.75 hours around an invisible companion whose mass is estimated at 6.6 solar masses, too massive to be a neutron star, and therefore almost certainly a black hole. The black hole's gravity distorts its companion and strips away its outer layers, producing a luminous accretion disk whose radiation revealed the system. Dozens of other stars lie in the vicinity, some of which may possess planetary systems. In the distant future, one of these stars could be captured by the black hole and share the fate of the present companion. Contrary to popular perception, black holes do not indiscriminately swallow all nearby matter.
At large distances, their gravitational influence is indistinguishable from that of any object of equal mass. Consequently, stable planetary systems could, in principle, exist around black holes. Such systems might form from the debris of the supernova that created the black hole, or from objects captured during close encounters with other star systems. Three principal classes of black holes are recognized. Supermassive black holes, with masses of millions to billions of solar masses, reside at the centers of most large galaxies and can power quasars visible across billions of light-years. Stellar mass black holes form from the collapse of massive stars and may merge, producing gravitational waves. Primordial black holes are hypothetical objects that may have formed in the extreme conditions of the early universe. Smaller ones would evaporate rapidly through Hawking radiation. Detection remains challenging. Methods include the observation of orbital motion of visible companions, the study of accretion disks, and gravitational microlensing. Rogue black holes drifting through interstellar space may also exist, but they are likely to remain undetected for the foreseeable future. Long before the invention of the telescope, observers noted a luminous band stretching across the night sky, the Milky Way. This striking feature inspired countless myths. Detailed study eventually revealed that it consists of the combined light of billions of distant stars, too remote to be resolved individually. In 1755, Immanuel Kant proposed that the stars surrounding us form a single vast system, and that certain nebulae might represent other galaxies. This insight was far ahead of its time. Observational confirmation of external galaxies came only in the early 20th century. In 1936, Edwin Hubble published the classification system still used today. According to this scheme, the Milky Way is a barred spiral galaxy. Our galaxy is relatively old. Stars in its central globular clusters are approximately 13 billion years old, while most objects in the thin disk formed around 8.8 billion years ago. Star formation, nevertheless, continues in selected regions. The galactic disk has a diameter of about 200,000 light-years. The surrounding halo extends considerably farther.
The Milky Way contains at least 200 billion stars, 100 billion brown dwarfs, more than 1 trillion planets, and vast quantities of dust and gas clouds. Ordinary baryonic matter accounts for only a small fraction of the total mass. Roughly 90% is dark matter, a substance that does not emit light but exerts gravitational influence. By analyzing stellar orbits around the galactic center, astronomers estimate the Milky Way's total mass to lie between 0.8 and 1.5 trillion solar masses. Our tour of the Milky Way begins at its center. This region is heavily obscured by dense clouds of gas and dust. However, a fortunate line of sight, known as Bod's window, allows clearer observation. At the galactic center lies the supermassive black hole, Sagittarius A star, with a mass of 4.3 million solar masses and an event horizon radius of approximately 16 million kilometers, 3 times smaller than Mercury's orbit. For decades, its nature was inferred from stellar motions and radio observations. On May 12, 2022, the Event Horizon Telescope collaboration released the first direct image, confirming the long-standing hypothesis. Within 3 light-years of Sagittarius A star, more than 6,000 stars have been catalogued. Some have well-determined orbits. The star S62, for example, approaches the black hole to within 177.8 astronomical units and reaches 6.7% of the speed of light. Relativistic effects cause the orientation of its orbital axis to precess by about 75 arc-minutes per revolution. Several massive star clusters, with a combined mass of roughly 1 million solar masses, are also present. Approximately 200 light-years farther out, observations suggest the possible existence of another supermassive black hole with a mass around 100,000 times that of the Sun. Moving outward from the center, we encounter the central molecular cloud, an irregular region 1,600 to 1,900 light-years across, with a total mass exceeding 60 million solar masses. This cloud contains numerous sites of ongoing star formation, gas nebulae, and protostars. Most of its material is molecular hydrogen, with temperatures ranging from 50 to 600 Kelvin. In addition to hydrogen, it contains carbon monoxide, methanol, and hydrogen cyanide. A short distance from the center lies the galactic bulge, a bright, massive, roughly elliptical structure, 10,000 light-years long and about 7,000 light-years wide, with a mass of approximately 10 billion solar masses. Its elongated shape forms the central bar, a 13,000 light-year bridge that connects the major spiral arms. At one end of the bar is the star cluster Stephenson 2, which contains Stephenson 2-18, currently the largest known star, with a radius 2,150 times that of the Sun. The probability of finding planets around such an extreme object is extremely low. Any that once existed were most likely engulfed during the star's expansion. The galactic center is densely populated with billions of stars and likely hosts a vast number of planets. However, the probability of encountering potentially habitable worlds here is lower than in quieter regions because of intense radiation and frequent gravitational perturbations. Astronomers, therefore, define a galactic habitable zone
an annular region between 22,000 and 29,000 light-years from the center, where conditions are considered most favorable for life. Even within this zone, stars can migrate thousands of light-years over cosmic time, so location alone does not guarantee habitability. Continuing outward, we reach the galactic disk, the most prominent and massive component of the Milky Way. It consists of a thin disk 1,000 to 1,300 light-years thick, with a radius of approximately 50,000 light-years, extending to 100,000 light-years at its outermost stars, and a thicker, more diffuse disk. The thin disk contains about 80% of the galaxy's visible mass and formed more recently. Mathematical models indicate that between 8 and 11 billion years ago, the Milky Way merged with another galaxy known as Gaia Enceladus. This event contributed billions of stars, large amounts of gas, and dark matter, and was largely responsible for building the thick disk. The most visually striking features of the disk are its spiral arms. The major arms of Centaurus and Perseus, the secondary arms of Norma and Sagittarius, and possibly a fifth arm associated with Cygnus. Within the arms, the density of stars and gas is significantly higher, resulting in star formation rates 5 to 10 times greater than the galactic average. Young stars initially form in open clusters, but gradually disperse and follow the arms as they orbit the galactic center. Traveling along the Sagittarius arm, we reach the Orion Spur, a 11,000 light-year-long branch connecting it to the Perseus arm. It is within this structure, 27,000 light-years from the galactic center, that our solar system resides. Looking from Earth toward the galactic center, one sees the Great Rift, a dark band caused by massive clouds of interstellar dust and gas with a total mass of approximately 1 million solar masses. Although nearly opaque at visible wavelengths, these clouds emit strongly in radio and infrared. They consist primarily of hydrogen with admixtures of ammonia, alcohols, and even amino acids, marking them as potential future sites of star formation. New stars, however, will not ignite there for a very long time. Beyond the disk lies the galactic halo, the most extended and least dense component. It stretches from 100,000 to 200,000 light-years from the center, but contains only a few percent of the galaxy's total mass. The halo is populated by ancient globular clusters, whose stars are more than 12 billion years old, and by large stellar streams. The Sagittarius stream, for example, consists of stars torn from a dwarf galaxy that the Milky Way is currently absorbing. A similar process is occurring with the dwarf galaxy in Canis Major, whose stars have already wrapped around the Milky Way 3 times. In addition to stars and clusters, the halo contains hot gas at temperatures of millions of Kelvin and an enormous dark matter halo extending up to 2 million light-years. This dark halo can be detected only through its gravitational effects and remains one of the most profound unsolved problems in galactic astronomy. The diversity of objects within the Milky Way is extraordinary. Some are commonplace, others are rare and unique. Every region of the galaxy holds unanswered questions. Solving them will deepen our understanding of the universe around us. Whether humanity will one day comprehend all the secrets of the Milky Way, only time will reveal. What is already clear is that our galaxy is a dynamic, evolving system of immense complexity and beauty.